Recording today because I'd like to, after we get done, I'd like to finish the recording after school and then post it so you guys can watch the rest of it. So matrices are a way to organize information in rows and columns. And not sure how much you've been given in terms of understanding on this, but rows are counted down. Columns are counted to the right. That's why I usually call it downright easy to identify rows and columns. And now I have my texting feature so I can do that. Down. Oh, I should use a different color because that's not easy for you guys to see. Each item in the matrix is called an element. Yes?
So you're saying like A and 2, that's an element?
Yep. Here's a matrix. Can you tell me what the dimensions of this matrix are? 2 by 3. 2 rows, 3 columns. What is the element in row 2, column 3? I'm going to use a comma to separate them so that you understand that the row is first and the column is second. What is the element in row 2, column 3? 5, you are correct. That wasn't too hard. Anybody not understand that? That's element row 2, column 3. Okie dokie. What do you think a square matrix is? Same rows and columns. That's exactly right. So that's a 2 by 3, just like we had a second ago. What's the next one? 4 by 2. Can I get a witness on that? Yep, good. Lastly, 3 by 3. What's so special about that one? Yes, Mr. Singh? It's a square matrix. Yep. There are some interesting things that happen with square matrices that do not happen with the others. Yes.
Do you always have to read a row and column?
Yes. So that we're always consistent. Always need to be rows and columns. Adding and subtracting is easy. All I do is subtract or add the corresponding elements. Now that's not going to be true when we get to matrix multiplication, but it is true for adding and subtracting. So 2, 3, 5, -1 plus 4, 7, 0, 8. This should be extremely straightforward. Yes, folks, you're just adding corresponding elements. So what do you get when you add 2 and 4? 6. Notice that since you added the first row, first column entries together, they go in the first row, first column of the final answer. So you fill in the rest of this.
Adele's new album. I feel like it's not the Adele. Okay, I recommend you listen to one song. My Little Love. Like listen to it as soon as school is out. I don't know if this is
Did you get Ariana's email about how we were going to grade you in class?
No, because you never responded to any of my
What?
We were supposed to come in the day, like you were sick, and the day you were supposed to come back, we were supposed to come in, and we had this whole thing choreographed out for you.
I did read that one, and at the time I read it, I wasn't feeling the greatest, so I forgot to respond to it.
I
I'm
didn't
sorry.
take it to heart.
Okay, good. All right, so hopefully you got 10 and 5 and 7. Did you?
Yeah.
Okay, great. Seriously, folks, that's as hard as it gets on the adding and subtracting. It's not tough. But there is a time when you can't add them together. What condition do you think would have to be necessary in order to actually be able to add them together and know it's not square matrices as the example I gave? Under what condition would you not be allowed to add? Well, you might not. Like you may say that if I had a 2 in the left corner and an A in the left corner, I might say the answer would be 2 plus A because I wouldn't know what to do with it. But that's about it. But that wouldn't stop me from adding them together. I get what you're saying, though. Oh, if the dimensions are not the same. And now I'm not saying that the rows and columns have to be identical like a square matrix, but you gave a good example. A 2 by 2 and a 2 by 3. You cannot add those together at all. If I put that on a test, it's a trap. You put no solution and you move on. Okay? Must have equal dimensions. So maybe I should type that out. Rows must be equal. Columns must be equal. I'm saying it this way so you don't get the idea that they have to be square matrices. I mean, obviously square matrices does qualify. Okay, on this next example, they're referring to what's called scalar multiplication. That is not to be confused with matrix multiplication. That's a whole different animal that we will get to as soon as we can. Okay? Scalar multiplication looks like we're taking a number and multiplying it times a matrix. So, this example says the city has a combined sales tax of 7.25%. What number do you think I'm going to multiply by this matrix to get the final answer? Stop copying. 1.0725, you are correct, both of you. no matter who is copying whom. Now, take your graphing calculator. We'll do a smaller example. What? All right, now, a few of you might have this, the matrix button might be in a slightly different spot. But for those of you with the newer style calculator, you can see the word matrix right here, right above the X inverse button. Now, some of you with the older style calculators actually have a button that says matrix on it. Yours is in the same spot. Anybody have the older style? No. You're not going to, you're going to have to do this the old-fashioned way. Okay. So go to the matrix section. It should look something like this. You might not have, dimensions on any of the matrices, but 60 would. Yeah. I lost my lung capacity, but my hearing's back. All right, now, you'll notice that I jumped over to where it said edit. Okay. I'm going to have to pause this for station identification since my... And so, with the matrices... I love this class. Jump over to where it says edit. Now, I'm gonna pick the first one. Since it's already highlighted, I'm just going to hit the enter button. Make it a 3x1 matrix with entries 1, 2, and 3. So make it a 3x1 with entries of 1, 2, and 3. And if you got any questions on how to do that, just let me know.
How long have you been teaching math?
This is my 26th year. Okay, now, you want to multiply that by 1.5? We're going to go back to the main screen, so I use the quit button right above the mode, so jump back to the home screen. Let's just multiply a matrix by 1.5. So I've got 1.5 times, remember where the matrix button was? This time, when you go back to that section, leave it where it is under names. And choose the matrix that you want. In this case, it's a 3x1 matrix, the one we entered. And so on the main screen, you see 1.5 times matrix A. And when you hit enter, it will do exactly what you told it to do.
That's some cool math. How did you get the editing thing back to
Use the quit, which is above the word mode. So that jumps back to the home screen. And then you type your 1.5 times and then go to your matrix and use the names feature. Okay. Wrong way. Okay. I was just, yeah? What? Don't mean to interrupt.
Oh, no, you're okay.
All right. Okay. What happens when you take 5 and you add 0 to it? You get 5. What happened to the 5? Nothing. Right? This number right here has a special property. It's called the additive inverse. Or I should say additive identity. Can you guess which number would be the multiplicative identity? What number can you multiply by and never change the value of the original number? 1. So, there's an additive identity and a multiplicative identity. Who is Charles K. Cow's 88th birthday? That's interesting. Do you think that there is an additive identity for matrices? Do you think that there is a matrix that I could add to this matrix and never change the value of the original matrix? If so, what would that matrix be? That would be what we call the zero matrix. And for a 2 by 2, it looks like that. Obviously, if it was a 3 by 3, it'd have more entries in it. But it's not really that hard to understand, right? Because you're adding 0 to every number. What number would you add to 5 to get 0? You would add -5. This is called the additive inverse. Additive inverse. Do you think that there's the same idea with matrices? So if you had 2, 3, 4, 5, what do you think the additive inverse would be so that you would come up with the zero matrix? There you go. Yes, you're smart. You're welcome. Told you the hearing's back. In a little bit, we'll talk about the multiplicative inverse. Okay? That might actually be part of the video that you watched tonight. Now, additive inverse. What do we typically call it? 5 and -5 are what? Opposites. That's typically what we call them, but additive inverse is the fancy term. Now, we need to understand matrix multiplication, and it is not as easy as the addition and subtraction. It's not hard, no. Yeah, I guess maybe I should do my... This first matrix is going to be a 2 by 2 matrix. That's a 7, sorry. It's a bad looking 7. The second matrix is going to be a 2 by 3 matrix. Now you'll notice that obviously I have not filled in all the values. There's a reason, because I kind of want to walk you through this. Before you can ever do this, we have to check something. We have to check, and if you go online, you're not going to find this term because I guess this would be a Staleism. The inside number rule. Can't spell. In order for you to even be able to do matrix multiplication, inside numbers must be equal. If those two things are not equal, what's your answer going to be? No solution. Then we have the outside number rule. Dimensions of product. The outside dimensions tell you the dimensions of your answer. So the answer to this question is going to be a 2 by 3 matrix. How many different values are in a 2 by 3 matrix? 6, right? So we're going to have the top row and the bottom row, but there will be 6 different entries in our answer. If I'm going to multiply row 1 of the first matrix times column row of the the second matrix, where do you think that answer is going to be in my final answer? I'm multiplying row 1 times column 1. Where? Come on, say it. Okay, where in column 1? If I'm multiplying row 1 times column 1, row 1, column 1. The very first upper left corner, right? Okay. We're going to multiply the first entry times the first entry, and that would be 8. And the second entry times the second entry, which is negative 21. And we're going to add those two things together. What do you get if you add 8 and negative 21? Negative 13, right? Okay, now I'm going to make a new row here. 1 and negative 3. Stay with the first row. Move to the next column. 2 times 1. 3 times negative 3. Nice try. 3 times negative 3 is negative 9. Now, I know you stayed with the first entry, and a lot of students do that. You can't. You must move. Right? That's why I'm drawing these arrows, to kind of connect things together. First entry times first entry. Second entry times second entry. If there was a third entry, I would just continue to move. Well, I mean, it is distributing, so that's kind of true. Okay, so 2 plus -9 gives me what? -7. Okay, I'm going to fill in the rest of this matrix, and then I want you to fill in the rest of the spots. Now, there are lots of places to make mistakes, so if you disagree with me, now would be a good time to speak up and see if I made a mistake. Sure. Yeah? Oh, no, they'll all be there. The reason I did it that way is just because I wanted you to focus on one row and one column at a time. That's what I was getting at. But no, yeah, everything will be given to you and when you're asked. Now, notice, folks, I didn't have you do that with a graphing calculator. That right there would be done by hand. Maybe a scientific calculator or maybe an I-step calculator, so that you don't make mistakes on the little tiny multiplication and adding. But there's no reason for me to hand you a graphing calculator on that and say, matrix A times matrix B, boom. Yeah, I'm sure it can do all that for you. But you need to understand the process of what it's doing. Any questions on this? I'm not going to worry about multiplying these out at the moment, but what I am going to ask you is this. Like, let's go down to this one right here, letter B. Does A times B exist? Does A times B exist? This is a 2 by 3, and this is a 2 by 2. So several of you are saying no. That is correct. AB does not exist for that example because of the inside number rule. Okay? Does BA exist? That's true. We could switch it around. Now, what does that prove? Don't listen to that kid. All right, now, you have been told your entire life that 5 times 7 and 7 times 5 both give you 35. That is the commutative property of multiplication. Guess what we just figured out? That does not work for matrices. Now, you will be hearing the rest of this video or watching the rest of this video tonight so that we can start working on 7.3 tomorrow. And then we will be going into... Okay, continuing on with these notes. Example 5, what they really are looking for here, they've got the different flower arrangements and the types of flowers, roses, carnations, and lilies. They've got flower arrangement 1, 2, and 3. And then we've got the prices. A florist can buy flowers from 2 different wholesalers, wholesaler 1 and 2, and wants to give all of his business to one or the other, so they're trying to decide between the 2 different wholesalers which one they want to use. So here are the prices in a format of, obviously this is a 3 by 2 format, and our original matrix was a 3 by 3 format. Now, if we want to find, so what they say at the bottom here is construct a matrix showing the cost of making each of the 3 flower arrangements from flowers supplied by 2 wholesalers. Well, if you take this matrix and plug it right up here, first of all, that would satisfy the inside number rule, right? the inside dimensions 3 and 3 would qualify. Wait a second. Did I do something wrong? 3 by 2. No. No, we're good. I'm just going to write down the first column so you can understand what we're getting at here. Now, since we know that matrix multiplication is row times column, let's just think about what we've got here. The top row of the first matrix are roses. Roses from arrangement 1, 2, and 3. According to the way we do matrix multiplication, first times first, well, that works because 5 is the number of roses and $1.50 is the price of the roses. But when I do 8 times 0.95, I have a problem because the 8 represents roses, but the 0.95 is carnations. It's the price of the carnations. So this actually won't work. So I'm going to have to get rid of this option. Well, okay. If you can't do that, could we put it in front? Well, no, that wouldn't work, right? Because then your inside dimensions are 3 and 2. So you couldn't multiply them together. Unless, what if I switched it and made it a 2 by 3? And I know you're probably going, well, you can just do that? Well, sure, we can, as long as we keep the information. All we're going to do is interchange the rows and the columns. So 0.59, or I'm sorry, 1.5, 0.95, and 1.3. So now when we do row times column, we've got price of the roses times roses, price of the carnations times carnations, price of the lilies times lilies. That actually makes sense. And then we're going to, after we multiply those individual things, then we're going to add them together. So we know that the outside dimensions give me the answer. So we're going to have a 2 by 3. And we would go through the process of multiplying those. I'll try to do the first one quickly. 1.5 times 5 plus 0.95 times 6 plus 1.3 times 4. 1840. So wholesaler number 1 is going to charge 1840 for arrangement 1. Okay, then obviously I'm going to take that and go to the next column and find the next value. And then the next column and find the next value. And then once I'm done with that, then I'll go down to the next row, which obviously is the $1.35, the $1, and another $1.35. And I will repeat the process with each column so that I can identify the bottom row values. And then I can make my decision on the wholesale. So we inverted the price matrix and put it in front and then matched it up. And that is not the only way you can do it, but I think that is a good way to do it. We could invert the 3 by 3 matrix with the roses and carnations, and then doing that, then we could stick that matrix behind. But let's not worry too much about that one. Okay, the identity matrix. This is a very important concept. The identity matrix, first of all, this is called the main diagonal. Oops, can't spell. from the upper left to the lower right, from the main diagonal. What do we notice on the main diagonal? We notice all ones. So if it was a 4 by 4, or a 3 by 3, or a 2 by 2, the main diagonal has ones. Everywhere else is a 0. This is called the identity matrix. Now, what's so special about the identity matrix? Well, this is called a multiplicative identity. Right here is the important part. I'll zoom in on it. It says matrix A, which could be any kind of matrix, times the identity matrix gives me the original matrix. Also, if you put the identity matrix in front of matrix A, you still get the same matrix that you started with. So what's that mean? Well, you guys know that 5 times 1 is 5, right? That means that the number 1 is called the identity for multiplication. This is the exact same concept. Since we'll be dealing with a lot of 2 by 2s and 3 by 3s, just keep that in mind. 1, 0, 0, 1. Basic 2 by 2 identity matrix. When you multiply it times any other matrix, now you have to be able to multiply them. You can't do a 2 by 2 and a 3 by 3 or something like that because of the inside number rule. Now, is there an inverse? Yes, there is. The inverse is found when you can multiply 2 inverses together, or 2 things together, whether you do it left to right, right to left, AB or BA, you still get the identity matrix. That means that B is what we call A inverse. That's how we read that, A inverse. So basically it's like saying this. A times A inverse equals the same thing as A inverse times A, which is the identity matrix. So how do I identify whether 2 things are inverses of each other? Well, we can do exactly what we just described. Now, once you understand how to find an inverse, you probably won't do it this way. But we're going to multiply this row times this column, right? So 3 plus negative 2. And what is that? That is 1. 3 times 2, that's 6. Negative 2 times 3, that is negative 6. When you add those together, you get 0. Oh, by the way, what happens in the upper left-hand corner if you ended up with a 5? Would you continue doing the rest of this? Answer, no. It has to be 1, 0, 0, 1, and if you end up with any other value, I mean, you can't have 1, 1, 1, 1. Folks, that's not the multiplicative identity. So, don't think it is. Okay, this row times this column, negative 1 plus 1, negative 2 plus 3. So we found that it was the identity matrix. Therefore, we know that these 2 things are inverses of each other. Now, how do I find an inverse? That's kind of the important part we need to know. This notation with the little -1 is showing me that they're looking for the inverse. First thing we need is something called the determinant. Now that is this thing right here, AD minus BC. But don't get hung up on memorizing a formula. Seriously. So I'm just going to pick a matrix, make one up here. 2, 5, -1, 3. Nah, we'll make it a -3. So how do I find the determinant first? Watch me draw these arrows. What is 2 times -3? That obviously is -6. Notice that I wrote the -6 above the upper left corner of the matrix. Next we have -1 times 5. That is -5. You know what? Okay, now we need to subtract. I circled it just because I want you to understand you are subtracting those two values. Now, what do you get? Well, -6 plus 5 gives me a discriminant, or discriminant. Gee whiz, that's in the quadratic formula. The determinant of -1. Now, once you find that determinant, you kind of hold on to it. The important thing is the determinant is not 0. If it was 0, something will happen. That tells you information. But it's not 0, so that helps us. The next thing we do is we take the elements on the main diagonal, that would be these two, and we literally switch places. We pick up the values and switch them. Okay? Not that bad. All other values in the matrix get multiplied by -1. So that makes -5, and that makes +1. The last thing we do is we multiply the entire matrix by the reciprocal of the determinant. Now, how do you write something as a reciprocal? 1 over that number. Now, in this particular example, you and I both can tell that we're talking about -1. Could I distribute the -1 inside and then get 3, 5, -1, -2? Yes, I could. This is correct, and so is this. Now, for reasons which shall maybe show up later, I would prefer that you leave your answer like this instead of pushing it. Because typically what happens is, like, you'll have 7, 5, 3, 1. Okay, you'll be finding the inverse of this. We got 7 minus 15. We get -8 as our determinant. Okay, and so then we switch the 1 and the 7. We multiply the others by -1, but they stay where they're at. And then the whole thing gets multiplied by the reciprocal of -8, which is 1 over -8. I don't want to see people pushing that fraction inside and making 4 tiny fractions. It doesn't make sense to me why somebody would do that. So I suggest you stay and leave it like this. And when we get to solving equations, you'll understand why I would not want you to push that inside, because it makes a mess. Anyway, that's how you find an inverse. If the determinant is 0, then you don't have an inverse, right? So I made that big deal at the beginning, because remember, you got to have the reciprocal of the determinant. So if the determinant equals 0, No inverse. Because you can't multiply by the reciprocal of 0. Because it doesn't exist. That's exactly what I just said. Under what condition does a matrix not have an inverse? Well, first of all, it has to be a square matrix. So keep that in mind. It does have to be a square matrix, but then the determinant cannot equal 0. If the determinant equals 0, that's when we have no inverse. So it must be a square matrix too. That's kind of an important detail. Determine whether the matrix has an inverse. Okay. So 6 minus 4 is 2. It does have an inverse. So if they want me to find the inverse, okay. So switch the 2 and the 3. Multiply the 4 and 1 by -1, but don't move them around. And then multiply the entire thing by the reciprocal of 2. There's your inverse. Now when we get to the 3 by 3, guess what we'd be doing? Graphing calculator. So back to the matrix section, and we're going over to edit, right? And we want a 3 by 3. And I'm going to have to jot my numbers down here because I don't remember. 1, 2, -1. Oops, not -2. 2, -1, 3, -1, 0, 1. So once you've got them entered in the computer or calculator, right? You made a 3 by 3. Got everything entered in. We're going to remember how we did the quit and we jumped to the home screen. This time when I go to the matrix button, I'm going to go over to where it says math. Now, which one of those things looks like it might be useful to you right now? The first one, DET for determinant. You are so right. Once again, now I'm going to go back to the matrix button. Remember how we leave it on names and we choose the one we want to appear on the home screen? I don't need the end parenthesis. It tells me that the determinant is -10. Now, we're not going to go into the details of how to show you that. I can show you how to find that by hand. It's not very fun. It is tedious a little bit, and you might make a mistake. So when we get to the 3 by 3s, we pull out the graphing calculator and let it do the work for us. Yes, I know you're happy about that. So we got -10. But that's not the answer to the question, right? I've got to find the inverse. Let's show you how to do that. So, matrix A, and then the button that, on my calculator that has the x to the -1. Now I hit enter. There it is. There is your inverse matrix. So not only are we going to find determinants of a 3 by 3, but with the calculator, we're also going to find the inverse. We're not going to do it by hand. I know I'm making you do it by hand with a 2 by 2, but that's because it's easier. C calc. Okay. Next. One of the things that we talked about, the big thing, properties of matrices, something that stands out is the fact that the commutative property is not true. Okay? And I guess I should take that back. It's true for addition. It's not true for multiplication. Okay, matrix multiplication is not commutative. That's the important thing. Now, all the other things that you normally think of, the identity property, the distributive property, the associative property, inverse, all that stuff is exactly the same. There's nothing new in any of those. So that's the only one you need to really keep in mind, is that matrix multiplication is not commutative. You can't just switch, and we talked about this before, AB, BA. I mean, we can actually find examples where one exists and the other one doesn't. So that's the important thing out of this whole slide. Everything else is, follows what you normally think of, what you've been taught since you were born. Now, we can use, and we will, we can use coordinates. We're not going to do this so much right now, but we can actually, you know what, I'm going to skip this for now. Don't worry about this example. We'll just say skip. And I think that takes us into the homework. So if you want to practice these problems, you can practice them to get to get better at doing these questions. Okay, but that's the basics of section 7.2, and I'll see you tomorrow in class.